Okay, let's dive into this. Welcome back to The Explainer. Today we're tackling something absolutely crucial for the modern world, and that's keeping our digital data secure as it travels across networks. Think about it. Every single time you send an email, buy something online, or text a friend, your data is zooming across cables and invisible wireless waves. But how do we actually make sure your private info doesn't just fall into the wrong hands? Well, today we're going to explore the nuts and bolts of encryption, weigh the pros and cons of different security methods, and then put your knowledge to the test. Let's get right into it.
So here is our roadmap for today. We'll start with the eavesdropper problem, then explain symmetric encryption, followed by the asymmetric solution. After that, we'll weigh symmetric against asymmetric and finish up with a quick knowledge check to lock it all in.
All right, Section 1, the eavesdropper problem, or how to keep secrets in a crowded room. Because to truly understand the solution, we've got to understand the threat first.
Imagine this for a second. You're standing in a really crowded room, wall-to-wall with strangers, and you need to tell your friend a highly sensitive secret. How exactly do you do it? I mean, if you just shout it out, literally everyone hears it. Well, sending data over any public network, whether that's a wired fiber optic connection or the Wi-Fi at your local coffee shop, is exactly like shouting in that crowded room. Your data's just out there, totally open and vulnerable to anybody who happens to be listening.
And unfortunately, there are people listening. In the networking world, an eavesdropper is essentially a hacker who intercepts data while it's in transit. Without any protection, sensitive stuff like credit card details, medical histories, or legal documents can just be scooped right up by these eavesdroppers.
So, when you type out a message or enter a password, that original, completely readable info is called plain text. It's raw, it's easily understood by humans and computers, and it is exactly what an eavesdropper is hoping to steal. To keep our secrets safe in that crowded room, we actually need to alter this plain text so that even if the eavesdropper grabs it, they have no idea what it means.
And that brings us to cybertext. By feeding our plain text through a really complex mathematical process called an encryption algorithm, we scramble it into ciphertext. This is your ultimate locked box. Now, to be clear, encryption doesn't actually stop the data from being intercepted. An eavesdropper might still snatch the data packet out of the air, but it stops the data from making any sense. To the hacker, it literally just looks like randomized, meaningless gibberish.
Okay, let's move into Section 2, Symmetric Encryption Explained, which is basically our single key defense.
Now, what's really interesting here is the sheer scale of the math. Symmetric encryption relies on a single encryption key. The exact same key used by the sender to lock the message is used by the receiver to unlock it. Back in the day, a simple shift cipher might just move letters a few spots down the alphabet, which a modern computer could crack in milliseconds. But today, we use 256-bit binary encryption keys. That gives us about 1.2 times 10 to the 77th power possible combinations. That number is so massively huge that a modern computer cannot just guess the key through trial and error. It would take longer than the universe has existed.
But wait, there is a pretty fatal flaw here. If the exact same key locks and unlocks the box, how on earth do you safely send that key to the receiver? If you just email or text the key, an eavesdropper could intercept it, and if they have your key, they can read all your encrypted data. This is what we call the key distribution problem, and it's the biggest headache when it comes to symmetric encryption.
So, how did computer scientists solve this? They had to get incredibly clever. That takes us to Section 3, the asymmetric solution, where two keys are definitely better than one. Asymmetric encryption introduces two totally distinct keys, a public key that you can share with literally anyone, and a private key that you keep entirely to yourself. Let's look at a quick story to see how this works in practice. Imagine Jane wants to receive a secure document from Tom. Step 1, Jane's computer generates a matching pair of mathematically linked keys. Step 2, Jane safely sends Tom her public key. Now, it does not matter if an eavesdropper intercepts this public key because a public key can only lock a box, it can never unlock it. Step 3, Tom uses Jane's public key to encrypt his document into ciphertext and sends it over to Jane. Finally, Step 4, Jane receives the document and uses her totally hidden private key to decrypt it. The eavesdropper is completely locked out. It's such an elegant and secure solution.
Which brings us to Section 4, Symmetric versus Asymmetric Encryption, weighing the trade-offs. You might be wondering, if asymmetric encryption completely solves the key distribution problem, why don't we just use it for everything all the time?
So, the crucial point is that it boils down to speed and logistics. Asymmetric encryption is amazing, but it requires heavy mathematical processing, which makes it significantly slower. Plus, think about the logistics of it. If you have a 5-person office and they all need secure two-way communication with everyone else, every single person must generate their own public and private keys and then swap public keys with every other worker. The complexity just explodes. Symmetric encryption, on the other hand, is lightning fast and super simple. So, in the real world, systems actually use asymmetric encryption just to safely send a symmetric key across the network, and then they immediately switch over to the faster symmetric encryption for the rest of the actual data transfer. Best of both worlds, right?
Let's move into Section 5, our knowledge check. Time to gamify your understanding. We're going to tackle Question 6 from the exam materials. I will describe a term, and I want you to try and shout out the guess before I reveal the answer. Ready? Let's go.
Here's your first one. A method of error detection. It is based on counting the number of 1 bits. Uses an additional bit, which is the most significant bit in the byte. Got a guess? Lock it in.
If you said parity check, you absolutely nailed it. By agreeing on either even or odd parity, the sending and receiving computers can easily flag if a bit was corrupted during transmission. Awesome job. Let's do another one.
Okay, here we go. A method of error detection. A value is calculated from a block of data and is sent with the block of data during data transmission. What do we call this calculated value?
And this brilliantly illustrates a checksum. The receiver recalculates the math when the data arrives, and if the checksums match, the data is safe and sound. Let's keep this pace up. Next question.
A data transmission method where data can be sent in both directions at the same time. Remember, this is the exact opposite of a walkie-talkie, where only one person can speak at a time. What is the term for simultaneous two-way transmission?
That would be full duplex, just like a modern broadband internet connection. Excellent work if you got that one. We've got one final rapid-fire challenge for you.
A data transmission method where data is sent 1 bit at a time over a single channel or wire. Lock in your final answer?
The answer is serial data transmission. Unlike parallel transmission, which sends multiple bits down multiple wires at once, serial takes it 1 bit at a time, which actually makes it highly reliable over longer distances. Let's bring it all together and see how this builds into a complete matching set for all the terms from that exam question. We even have 2 extra bonuses here. Data arriving out of sync is known as skewed data, and the industrial standard for serial connections is the Universal Serial Bus, better known as USB. Definitely feel free to pause the explainer right here if you want to lock these definitions into your memory for your exams. As we wrap up today's explainer, I want to leave you with a pretty wild look into the future. We talked about how those massive 256-bit keys protect our symmetric encryption today. But with ultra-fast quantum computers on the horizon, even those keys might one day be cracked. So, what's the next frontier? It's quantum cryptography. This actually uses the physical properties of light, things like photons and qubits, to create completely unbreakable codes based on the literal laws of physics rather than just really difficult math. How wild is that? Thank you so much for learning with me today. Keep asking great questions, keep reviewing the material, and I will see you in the next explainer.